Good evening, everybody. Hope you're all doing okay. All right, so we've got a couple things to talk about before we get into anything new. One is a mistake. Um, by the end of these things, I guess my brain is just done. So, um, this thing that I sent you off with last time, finding the isomers of this, there are not 5. There are many, and the reason for that is, and we'll look at both of these, is what I actually meant to write here is C6H14. I don't know why I said C6H10. I think because we were doing something with C4H10. Yeah, I think I got confused. I just had that in my head. And so this should have been C6H14. Anyway, if you tried it, I got some notes from people, and you got some good answers. There are a lot more isomers of C6H10 than there are C6H14. There are 5 isomers of that, and we're going to look at both of those together tonight. So, hey, Jennifer, Maria, Joey. The other thing is I had a question about how to do log calculations. So going back to the acid-base stuff, since that's in this homework too, I thought we could talk about that really quick. So I found see if I can get it to work here. No, that's the chat. I found a graphing calculator, like online simulation. Hey, Alyssa. Hey, Renette. So let's see if I can make it work and show you how to do this. All right, yeah, so here it is. So the question is like, when you want to find the pH, let me take this off for a second. So this is just a little bit of an aside here from the organic stuff. If the hydronium ion concentration is like, what was the example we were looking at here? 1.2 times 10 to the minus 3 molar. How do you find the pH? Well, you have to take the negative log of that. And depending on the type of calculator you have, it can work a little bit differently. So I think when I demonstrated it on my computer, I had a scientific calculator up there. And a standard scientific calculator only has room for numbers on its screen. So you type the number first, and then you type log, and then you push the button log, and then you get the log of that number. But a graphing calculator or a slightly more advanced scientific calculator like the TI 30 something that is like really common one, that one actually you can put letters in the screen, and so that means that you can put the log instruction first. So you can type it out like you would write it on the screen, like negative log of something. So let me show you what that looks like with this example. I realize your particular graphing calculator may not be exactly the same as this one, but I think the idea is the same. So let's see if we can get it to work. I haven't actually used this before, so I don't know if it's going to work. Let's see what happens. All right, so let's see what happens if I push log. Nothing. Oh, you know what? We probably have to go to calculation. Okay, so now we're on calculation. So I'm going to try to type this in as an entire expression. So I think this is the negative sign. Oh, that's a comma. Hold on. Maybe they just use the minus sign. I know on the TI calculators there's a difference between the minus key, like when you're subtracting, and the negative key, which is down like on the lower right, I want to say, like next to the period, like where this thing is down here. So I'm going to go negative log, and then I'm going to put my number inside the parentheses. So in this case, my number was 1.2 times 10 to the minus 3. Now, most of these calculators, including the TI ones, have a shortcut for scientific notation. So here, I believe it's over here. It's usually, all right, this one doesn't have the same one as the TI ones do, but we can try. So 1.2, they have this key over here, times 10 to the, and then we're going to write minus 3. Let's see what happens. Yeah, and so then we've got our pH. I'm hiding it, but it's like 2 point. I can't make that scroll away. It's 2 point. Here, I can just hit enter a couple more times. Now you can see it. It's 2.920819. So the idea with the graphing calculators is you put the number inside the, so you type negative log, and then you have the number inside the parentheses. So if you have a graphing calculator, try that out. Yeah, on the TI, it's that one next to the period. And the so for Jennifer's question, sort of the pH and the pOH is always 14. So this number up here plus the pOH is 14. I'll have to check that question, Alyssa. An acid gives protons and not H plus. H plus is a proton, because hydrogen is hydrogen has one proton and one electron, a hydrogen atom. So if it's H plus, you remove the electron, and then all you're left with is a proton. So H plus is a proton. So maybe check that wording again. But I'll pull up the Mastering Chemistry so we can look at that as well. Okay, so the other thing that comes up sometime, the other issue is typing the scientific notation properly. So all of this times 10 to the whatever, that sometimes is an issue with the TI calculators. So for the TI calculators, like whatever, the 84, whatever, all those, there should be a key that says EE, like 2 capital letter E's. And mine is at Harper, so I can't show you mine, but there should be that thing. And what that key means, that means times 10 to the something. So what you do, like if we wanted to type in the 1.2 times 10 to the minus 3 on that style of calculator, try typing 1.2 and then hitting this button, and it gives you like a small capital E like that, and then type minus 3. And that means 1.2 times 10 to the minus 3. So if you want to type in this whole expression, you would type in negative log 1.2 with that EE button minus, or not, it doesn't go up like that, it's just full size, minus 3, and see if that gets you the right answer if you do it that way. Notice that this is not a lowercase e. Lowercase e is a constant, 2 point something, and that is not what we're talking about. It's this capital, it's like 2 capital E's in a row. See if you can do it with that one. Okay, great. Okay, I'm going to log into Mastering Chemistry. While I do that, if you could, since I got this one wrong before, see if you can come up with, just right now on whatever whatever you have to write with, see how many isomers of C6H14 you can come up with while I'm getting into Mastering Chemistry. almost there. Okay, I think I'm in. So hopefully you've gotten a couple. I'll go through these questions first. Okay. All right, so this is number 14. For part B, it gives you the structure here, and then you've got to draw it. And I think the issue is that I know a couple of people had is if you're reading here, it says draw the molecule, identify the appropriate carbon chain by selecting each atom and assigning it a map number 1, 2, 3, etc. until all the atoms in the chain are mapped. So it's not enough to draw the just draw the molecule. They want to know that you actually can draw with those blue numbers on it. So you can draw the molecule. And this is probably wrong. I mean, it's certainly wrong. But just as an example, and then you go to a particular atom in that molecule and you right click and go to atom properties. And where is it again? Maybe it's over here. Uncheck the box on the map, and then so I'm going to put 1 there, and then I've got my 1. And then I can go to the next one, atom properties, and change that to 2. And now I've got 2. Now this is not the correct answer for this problem, so but that's the procedure to do that. Okay, let's look at the next one. Yeah, no problem. So what was the next question? 21. Part B. All right, 21 part B says, again, to make this a condensed structural formula. So you have to, actually, wait, let me see what the original one looked like here. All right. So you have to put this into a condensed formula. So in this case, you would have 3 carbons, and then the hydrogens go with the carbon that they are attached to. So in this case, it would be CH3, CH2, CH2, and then OH. And then we have to get those 3s in subscript also. So you can type them in subscript as you're going, or you can do it afterwards like this. And so it should look something like that. All right, and then yeah, so you'd put the O after that carbon that it's connected to. All right, question 8 was one that I got requested from a couple people too. So let's take a look at that one. So back to acid-base stuff, which solution is most basic? The most acidic solution is going to have the highest hydronium concentration and therefore the lowest hydroxide concentration. So the most basic is going to have either the lowest hydronium concentration or the highest hydroxide concentration. And because that's all fairly confusing, the easiest way to do that is to convert all of these numbers to pH. So let's do that. Or at least estimate. Here. All right, so if we've got these three choices, remember, I'm not gonna bother getting my calculator back out because I already put it away, but we can estimate this. So if the OH minus is 2 times 10 to the minus 6th, then the POH is going to be somewhere around 6. And that means the pH is somewhere around 8. Now, if you've got your calculator handy, you can just plug that in and do that negative log and not worry about it. But I'm just going to estimate. If we're 6 times 10 to the minus 9, and this is now the hydronium concentration, that means my pH is around 9. Actually, it's 6 times 10 to the minus 9th, so that's probably going to be like 8.5-ish. And the POH, you know what, this is confusing. Let's keep these in order. And if we already have the pH, we don't really care about the POH anyway, so whatever. All right, so 3 times 10 to the minus 4, that's going to give us a POH of something just over 4, something like between 4 and 5. And that means that the pH is going to be like around 10. And then this bottom one, the pH is going to be something less than 10. So this one's probably going to be greater than 10. This one's probably going to be less than 10. So this is a better answer. Now, obviously, these are hard. These look the same the way I wrote them here. So you would want to put them in your calculator so you can get a more precise measurement there. Oh, wait, you can't see anything I'm doing. Sorry. Okay. Yeah. So anyway, that's what I was doing. Wouldn't the second one be the second answer? What do you mean? The bottom two, the third and fourth one here, are the most basic in general, and I think overall the third one's going to be higher if you actually calculate those. All right, and then looking at number 23. So here's number 23. Draw the molecule. So we've got this molecule here, and then there's some other ones as well. And this is dealing with those condensed structures that only go in one line. So if you have a condensed structure that has these parentheses in it, like this first one here, what those parentheses are saying is that whatever is inside there is branching off of the adjacent carbon. And then we have to use our good chemical sense to make sense of that. Now, generally by convention, it is branching off of the carbon just that it's just after. But if that doesn't make sense chemically, like if this happened to be a CH2, then we'd know that it would have to be the other one instead. So we always have to use our sense of how many bonds carbons are supposed to have to figure this out. So in this case, can't do it with my pen. So I'd have my 4 carbons like that, and then there would be one more coming off of the second carbon like this. So the first CH3 is here on the left. This is the CH. This is the CH3 coming off of it from the parentheses, and then CH2, and then CH3. All right, so same idea with these. In this case, you have a double bond to oxygen there. That one's drawn out explicitly, so you just put it in there. And then here, you have also in parentheses, but this time it's a 2-carbon group in parentheses. So the CH2 and CH3 have to be coming off there. And if this is confusing to look at this way, one thing that can be helpful is drawing it out in like a kind of condensed format where you're still using CH3, CH2, CH, but you draw lines between them like we did on Tuesday. Let me show you an example of that, like this up here. If you draw it out in that style first, that can help you get to the line structure rather than trying to figure out what that line structure might look like by only looking at the single line one. So try that out, and if it's not working out, if you're not getting it, let me know. We can talk about it more. Okay, let's take a look at our isomers. So we'll do these isomers of C6H14 first, and then we'll go back and look at C6H10. So for C6H14, we need 6 carbons, 14 hydrogens. And there's a couple ways you can do this. You can draw it out completely the whole time, or you can sort of play around with the carbons first and then add the hydrogens afterwards. You can also just stick with line structures, but we have to be a little bit careful to always keep track of hydrogens when they're not explicitly shown. So I've found a lot of people like to, when you're trying to find different isomers, a lot of people like to start with just carbons. So like, for instance, we might express one like this. Now we know this isn't actually a valid way of expressing a molecule because that's not what it would look like. We have to account for the hydrogens too, but that might be a way of at least thinking of it first. And then we can always draw it in a line structure if we want. Make sure we have the same number of carbons. And then we just want to like kind of count our hydrogens and make sure we've got as many as we want. So we want 14 hydrogens, and that looks like 14 to me. So that works. I don't want to draw in all the H's. Again, if you don't draw in all the H's, this is not really a correct structure. It's not a correct Lewis structure, but we're not worrying about that right now. We just want to find these different isomers. Now, as we talked about last time, we can't just twist this thing around because that would give us the same structure. That would end up with the same molecule. So to find new isomers, we want to pull the carbons apart and stick them back on in different ways. So some other possible isomers you could find might look like this. So maybe we pull one off the end and we stick it on the second carbon. Maybe we pull one off the end and stick it on the third carbon. Again, let's draw those as line structures. So this time we're going to have a 5-carbon chain with another one coming off of the second one to the right. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then this carbon is coming off of the second one to the right. Notice I draw that up instead of down because we want to preserve those fairly wide bond angles of about 110 degrees, those tetrahedral bond angles. So if it goes down, it kind of like looks squished, and that's not the best way to draw those structures. I don't know that it's technically wrong, but we would generally draw it like this. And then this one with the carbon coming off of the middle carbon might be like that. And then what if I follow that problem, or follow that pattern? If I follow that pattern and I put the carbon, kind of move it over one more, this is now wrong. What's wrong about this? Why is that not one of the 5 isomers? Yeah, yeah, Alyssa, you're right. It's not only too similar, it is exactly the same as the second one. So take a look at these two. The second one up here, this one, and then this one we just drew. Imagine taking this one and simply flipping it over. If we just flipped it over, we'd have this one, right? Or if we rotated it around and like twisted it a little bit, we'd have this one. So without physical models, how would you necessarily know that? Well, one way is to remember that you can always start counting your carbons from either side. So we might think of this one as 1, 2, 3, 4, 5. This is coming off of the fourth. 1, 2, 3, 4, 5. This is coming off of the second. But we can count from the other side and get the same thing. So if we count from the right on this one, we'd go 1, 2, 3, 4, 5. And that extra carbon is coming off of the second carbon, just like here. So you can always start that counting from whatever. It's totally arbitrary. And so these are the same. And this is a really common mistake in trying to find isomers, is finding two that are the same and saying that they are different when they are in fact not. All right, so if those are the same, then this is not a fourth isomer, and there are in fact two more. So the other two we can't find by simply moving that one carbon around. So what we can do is take another carbon off and now have two carbons to put in some different places, and see if we can find those. So what if we started from this one, but we took this outer carbon off and like stuck it on over here or over here? That's how we get to some additional isomers. All right, so I'm going to start with that 4 carbon chain, one coming off here, and I can put another one there. That's definitely different because now I don't even have a 5 carbon. I don't even have 5 carbons in a row anywhere. No matter where I start or stop, I always have just 4 carbons in a row. So that's another isomer. And we would draw that one like this. So we would show both of these carbons coming off of right here. And then for the fifth one, this is where it gets hard because as you pick out some of the easier ones to find, it becomes harder to find one that is totally unique. Like, for example, let's say I use that same philosophy. I pull that extra carbon off, or that same idea. I start with this one. I pull the extra carbon off the end, and I stick it on here instead. That looks nice, right? Looks pretty different from all these other ones. I mean, you can't see it. Looks pretty different from all the other ones. I might draw it in a line structure with 4 carbons and then like 2 more coming off of here. But guess what? That's the same as this one, right? 5 carbons, 1, 2, 3, 4, 5, with 1 more coming off of the middle of the third one in. Move this up a little bit. 1, 2, 3, 4, 5, with 1 coming off the middle one. So that one is also the same. So that didn't work. The way to find the last one is if we move that one, that extra carbon over here. That now becomes a new one. It looks like that. And those are the 5 isomers of C6H14. All right. Now, you noticed I kind of did some trial and error there. Not that I didn't know what the isomers were, but that's how this is done. It's not reasonable to expect that you just write down all 5 isomers on your first try. It's reasonable to try some things and then try to figure out which ones are the same as before. And as you may have seen on the homework, or you will see on the homework, the general way that we'll ask questions about this is not just to say find the 5 isomers, but to give you some structures and ask, are these the same or are they not? Or like a multiple choice question that is pick the 2 structures that are the same, and it'll show them in some different orientations and then ask you which one is the same. Sorry, answer another question here. All right. So now let's go to our other, what we had here, what I originally asked you, C6H10, because that will kind of lead us into the next thing. And here's where line structures can sometimes cause some problems. So if we're only dealing with the carbons, yeah, number 37 on Mastering Chem is that example. So if we're only dealing with the carbons and we're thinking, oh, what are some different ways that we can make 6 carbons? You'll notice that, as we just did, all of those were examples of C6H14, not C6H10. And if we were only doing this in line structure, it would be even harder to get that right, because we'd look at this and go, yeah, 6 carbons looks great. We have to count up all those hydrogens that aren't even there to find out that we don't have C6H10 here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And so these are, this is C6H14. And so how do we find C6H10? And I've talked to a couple of you over the last couple of days about this, and you came up with some solutions. How do you remove hydrogens from a structure without violating the rules about how many bonds carbon can have, for example? And the way you do that is to add either multiple bonds, so double bonds or triple bonds. So watch how that works. If we have just a very simple 2-carbon molecule, ethane, and we add a double bond to it between the carbons, well, now those carbons have 5 bonds each. So they can't have that many hydrogens. So we need something like that. And that line structure would actually be like just like that for that example. So if we add multiple bonds, we can take away hydrogens. And that's why that's one reason why C6H10 can have so many different possible isomers. So if we started with C6H14, every time we add a double bond, we take away 2 hydrogens, right? We went from C2H6 to C2H4. So C6H14 to C6H10 means we need 2 double bonds, and there are a lot of ways that we can do that, right? We could go here and here, whatever. So actually, I don't want to go too fast here. Let's draw those hydrogens in so you can see how that works. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. So great. And then if we draw that line structure, we have a double bond between these 2 and then moving over between these 2. So that's one possibility, but you can imagine there's many more. You can have a triple bond instead of two double bonds. You can have the double bonds in any position. You can use any of those isomers that we found before and just add double bonds somewhere, wherever. So you can imagine there's quite a few more. And then beyond that, there's actually another way to reduce hydrogens, and that's called cyclic alkanes. So if we have to make them a little bit bigger here, but if we had, let's say, butane, so that is C4H10. What happens with a cyclic alkane, if you imagine this in pieces again, is rather than pull a piece off and put it on somewhere else like we were doing with isomers, we can actually remove hydrogens from the ends and connect those to each other. Now this is going to look messy. That's not the way that you would draw that, but that's the idea. The way you would draw that is to connect them together like this. In a ring, and this is now C4H8 instead of C4H10. And so that's called a cyclic alkane. So you could do the same thing over here with our C6H10. We could put those in a ring. And cyclic alkanes actually have their own names that are based on the names that we've already learned. So this one, coming from 4 carbons, which we call butane, this molecule is known as cyclobutane. And in a line structure, it is just a square, like that, C4H10. So we could also have the smallest possible cyclic alkane is cyclopropane. Which is C3H6. And then we've got cyclobutane. If we keep adding carbons, we've got cyclopentane with 5 carbons. Cyclohexane with 6 carbons, and so on. So this would be C5H10, C6H12. So if you took cyclohexane, C6H12, and then you added a double bond in there somewhere, then you'd have C6H10. So that would be even another possibility. You could have cyclopentane, you could add a double bond and then add another carbon sticking off the side somewhere. That would also be C6H10. So there's a lot of options there. You could use cyclic alkanes, you could add multiple bonds. And then you'd want to find out if those isomers are the same, the ones that you draw, or not. Notice, and this is another kind of tricky thing, cyclohexane not an isomer of regular hexane. And that's confusing because they have the same name in them, right? Hexane, cyclohexane. But remember, hexane was C6H14. Cyclohexane is C6H12. And the definition of isomers is they have to have the same molecular formula. So if one of them has 12 hydrogens and the other one has 14 hydrogens, those are not isomers. Those are unrelated molecules. Even though they have the same name, they're not isomers. They're not really related, except that they have the same number of carbons. Okay. So that brings us to Functional groups. You're going to like this part. So you may have seen this on the objectives for the chapter. Identify these functional groups: alkyl halide, alkene, alkyne, alcohol, thiol, ether, aldehyde, ketone, carboxylic acid, ester, amide, and amine. It sounds a little daunting. I know that. I realize that. But the good news is that this is just memorization. You all love memorization, right? I mean, it's like anatomy and physiology. You do way harder memorization than this. This is where you just get your flashcards out and you just remember the name of the thing. When we were revising this course a couple of years ago, we talked at length with people in health careers, in nursing, in dental hygiene, and a lot of these areas that you all are going into. And functional groups was one of the things that they kept saying, oh, you have to do this, you have to do this. Make sure they know this stuff because there's going to be a lot more of that in those professional programs. So functional groups are the parts of a molecule that determine its reactivity. So what thing in the molecule, what little bits of atoms actually go do the reaction, actually interact with other molecules? Those are the functional groups. And being able to identify them then leads to eventually, especially if you go on and take organic chemistry as a full course, it leads to being able to predict reactions, because you can say, well, this molecule has this piece and this molecule has this piece, and we know those pieces go together in this particular way. And it's pretty predictable like that. So what we've learned so far are the alkanes. An alkane is technically a functional group, but we said it was just C and H, no double bonds. All the stuff we've been looking at so far would be in the alkanes. And actually, alkanes are pretty unreactive. They can combust. You can burn them in oxygen. They can do a couple other reactions, but they're generally considered not very reactive. So they're used for solvents and things like that. So the functional groups are going to be pieces on molecules that do actually have some reactivity. So let's set up a name. Let's set up another table for this. We'll have a name of the functional group. The general structure, so what is it that makes it that functional group? And then an example, or maybe a couple examples. So what's a molecule that has that functional group? All right, so we'll start with alkyl halide. An alkyl halide is where we have some carbon-containing molecule, some organic molecule that is connected to a halogen. That's where halide comes from. Remember, the halogens are fluorine, chlorine, bromine, and iodine. So for general structure, we're going to use some what we call wildcards. We're going to draw Rx, and let's talk about what that means. So in this case, X is one of the halogens, and R let's not use another X, that's confusing, is something. R is a common wild card for organic chemistry, and it just means some carbon-hydrogen stuff. It could be a big molecule, it could be a little molecule, just carbon something. That's R. So we're going to use R in this whole table. It just means general carbon stuff. So an example structure might look something like this. Or we could make a cycloalkane, since we just learned about those. We could have a couple different halogens on there. Well, in that case, they're both the same. But just any carbon stuff that also contains halogens on there is called an alkyl halide, and can do some special reactions because of that. Is what the C and the CH? I guess I don't understand that question. Oh, the bond in the R here. So no, so this R would be like, all right, so let's look at our example. So if we look at this one here, this thing with the chlorine, yes, the halogen binds to the carbon. So in this case, let's draw this. This is R, and then this is X in this case. So R is just like the big carbon chunk, and then X is the halogen. That's why I drew it generally like that. All right, next on the list is alkene. Alkene is a carbon-carbon double bond. So obviously carbon has to connect to more stuff than that because it needs 4 bonds, but anything with a double bond is called an alkene. That's an alkene functional group. Again, we can have straight chains, we can have rings, we can put them wherever we want. And alkenes are more reactive. So when you see an alkene in a molecule, then you know that that part of that piece or that bit of the molecule is going to go out and react with something else, or is likely to in certain situations. If we change that E to a Y, we have alkyne, and that is a triple bond. So triple bond between 2 carbons, which means there's only going to be one connection on either side. Now with alkynes, if you remember back to when we were talking about molecular structure, we said that if you only have 2 things connected to an atom, then those things are going to spread out as much as possible and they're going to be linear. So rather than having the zigzag structure like this, when we have a triple bond, we can have our zigzags like normal, but then that triple bond is actually going to be straight in line. So there are if we're going to label our carbons here, 1, 2, there's a carbon on this side of the triple bond. Sorry, move that up. And this side, on the left side, and then carbon 5, 6, 7, and 8. So there's 8 carbons here, but 3 and 4 don't zig and zag because alkynes are straight. They are 180-degree bond angles. For that reason, it's extremely unlikely, it would be very strained to try to fit that inside a small cycloalkane like that. So cycloalkynes have to generally be bigger, have to have more carbons so that there's room for that straight bond angle to exist. All right, so next we've got alcohols. So outside of chemistry, we think of alcohol as a specific substance, which is ethanol. But of course, there's a rubbing alcohol, which is isopropanol. There's different alcohols. Alcohol in general just refers to an OH functional group. So just like before, we have some carbon stuff, and that has an OH on it. So that might be something very simple like ethanol, which is the alcohol that we drink sometimes that's fermented from sugars. Then it could be something like this, which is isopropanol, that's rubbing alcohol. And it could be quite complicated. I'm not going to draw it here because I don't know it off by memory, but something like cholesterol that also ends in -ol has OHs on it. It's a big molecule with a bunch of carbons and a bunch of rings. But you can have larger things that also have OH on them. We can have interesting structures like this, known as phenol. I don't know if they use them much anymore, but I can't remember the name for it, but the red soap for like scrubbing for for like making sure that that your hands are sterile from back in the day. That was this stuff here. I think it starts with a C. I don't remember what the name is. And then related to alcohols, we have thiols, which are same as alcohol but with sulfur instead of oxygen. Thiols tend to be quite stinky. So a lot of I mean, there's lots of different functional groups that smell, but some of the really kind of like rotten egg, fart kind of smells are thiols. We think of them as sulfury smells, but sulfur actually doesn't smell. It's when sulfur and hydrogen are together that you get those really bad smells. And then our last functional group of this type is the ether. Which is an oxygen in between two carbons. And I'm going to put a little dash there, a little apostrophe. This just tells us that this R on the left doesn't have to be the same as this R on the right. So we can have something like this where they are the same. This is diethyl ether. That is what we often refer to as just ether. It's a common organic solvent we use in the lab. It used to be used as an anesthetic a long time ago. It's not great, and it's pretty bad for you. So I would not. It's not in use anymore. Some people, I think, inhale it like as a drug. It's not a good idea. It can really hurt you. But you can have something like this. You can have different size carbons on either side. You can have ethers inside of rings, which are common solvents, like this one known as THF, tetrahydrofuran. Those are all examples of ethers. Okay, our next part of the table here, we're going to give its own category. And we're going to call these carbonyl functional groups. A carbonyl is a carbon double bonded to an oxygen. And so all of these functional groups from here on down involve that group, but they all have their own name. And this is often where some of the confusion goes with functional groups because they look pretty similar. And so you really have to keep an eye out for the differences in these groups. So we'll start with aldehydes. So things like formaldehyde. An aldehyde is going to have an R connected to the carbonyl, which is that carbon double bond oxygen. And then on the other side of the carbonyl is a hydrogen. So it's not any carbonyl. It has to have a hydrogen on one side. So that's something that can't really be inside of a ring. You can have the simplest aldehyde is formaldehyde, which is this. But you can also have longer chain molecules that happen to have that functional group. Aldehydes can also be pretty stinky. They can also smell nice as well. In fact, there's a whole category of fragrance molecules that are often used in perfumes that are known as aldehydes, like even on the labels, not just for chemists. Sort of those classic old perfumes like Chanel No. 5 or something like that, like where you think about stuff your grandparents or great grandparents would have worn. Those are often aldehydic in smell. So a closely related functional group to the aldehydes are the ketones, and ketones look very similar. The difference is instead of having a hydrogen on one side, they have more carbon on the other side. And again, it doesn't have to be the same as the carbon on the other side, but that's why. But if it's carbon on both sides of that carbonyl, then that's a ketone. So like one that we use often in lab is this one, acetone, which has 3 carbons. Because those can be on either side, then that means that the ketones can be inside of a ring. So something like that, it's got carbon on either side. That makes it a ketone, not an aldehyde. Let me know if these distinctions aren't clear. We can go back and talk about it. All right, our next carbonyl-based functional group is carboxylic acid. Carboxylic acids have, again, carbon with a carbonyl, but then they have an OH. And these actually are acidic. So this hydrogen here is pretty easily donated, and that makes these an acid. So when we talk about like acetic acid, is this. You can also have much more complicated acids, but like the aldehydes, if you're going to have a bigger molecule, this part still kind of has to be hanging off because you have to have the OH here. There isn't any way to connect anything else right there and still have it be a carboxylic acid. So if you're going to have something like a ring, this is a common acid called benzoic acid, and it's got this this carbonyl part here, and then the carboxylic acid part is the whole thing. So the functional group in this case is the entire thing here, not just the carbonyl. These all have carbonyls, which is the carbon double bond oxygen. It's the whole rest of it that makes it the specific functional group that we're naming. All right, moving on from there, we have the esters. An ester is very similar to a carboxylic acid, but instead of having an OH, it has an O with then more carbon attached. So you could have an ester something like this. You could also have this one inside of a ring, which is sometimes called a lactone, but you don't have to know that, so I'm not going to write it down. But something like that would be an ester. This is an important part of a lot of biological molecules as well. And esters tend to be good smelling. So a lot of the like fruity smells, minty smells, things like that are often esters. All right, and then our last carbonyl-based functional group is called amide, A-M-I-D-E, or sometimes pronounced amide. Either way is fine. And amides are similar to esters, but instead of oxygen, they have nitrogen. And the two things connected to that nitrogen can either be more carbon stuff or hydrogen. So I'm just going to leave those blank because it could go either way there. So this is really important bond because this is the bond that connects amino acids together in proteins. So it's sometimes also known as a peptide bond. You have the C double bond O from the acid part of the amino acid. You have the N from the amine part of the acid. They connect and you make a peptide bond, and that's what proteins are made of. So when we get into the proteins chapter, talk a little bit more about biochemistry, we'll see that happening. So again, for some examples we can draw, so we can just draw something like this that has hydrogen. We can draw something where there is carbon connected to that nitrogen. We can draw something where there are multiple carbons connected to the nitrogen, 2 carbons connected to the nitrogen. That. And then our very last functional group that you need to know, once my computer comes back here, is not, so I'm going to put a little line there because it's not a carbonyl-based one. They are the amines. So instead of a D here, they have an N. Instead of amide, they're amines. And those are nitrogen-based things as well. So just without the carbonyl. So amino acid, it comes from this. You can have kind of smaller amines like this. You can have amines that have multiple carbon things coming off of them like that. Those are all examples of amines. And this can be a source of trouble. If there's a carbonyl next to it, it's not an amine anymore, it's an amide. So watch that distinction. All right, the last thing we're going to do tonight with functional groups is talk about primary, secondary, and tertiary functional groups. And then we'll save the reactions part for until Tuesday. So we're generally, when we talk about these terms, we're generally talking about alcohols, halides, and amines. Sorry, my computer's slowing down, so it's like making the words, making it harder to write. And the symbols we use for primary, secondary, and tertiary are 1 with a little circle, 2 with a little circle, and 3. So like first degree, second degree, third degree. And it's a measure of how many carbons are attached to that particular functional group. So let me show you what I mean by that. If we take a molecule like this alcohol is connected to a carbon that has only one other carbon connected to it. So I'm going to circle that. This alcohol is connected to a carbon that has 2 other carbons connected to it. And then this one is connected to a carbon that has 3 other carbons connected to it. So we call this first one a primary alcohol. We call this one a secondary alcohol. And we call this one a tertiary alcohol. And so if you imagine that oxygen could be also a halide, like a chlorine or bromine or something, you have the same thing. You can have a primary halide, a secondary halide, a tertiary halide. The difference comes in the amines, because nitrogen can have more than just 2 bonds. So a primary amine looks a lot like a primary alcohol. But a secondary amine means that you actually have more carbons on the nitrogen itself. And then a tertiary amine, same thing. There's more on the nitrogen itself. Like that. Yeah, let's go back to that primary alcohol. So the primary alcohol is such because the carbon, so here's, I guess, the first step. Yes, the alcohol is the functional group, but oxygen is always going to have just 2 bonds. And if one of those bonds is an H, it's an alcohol. If both of the bonds are carbon, then it's actually called an ether. It's not an alcohol anymore. So when we talk about a primary alcohol, we're looking at the carbon that the OH is connected to, and then we're asking how many more carbons are directly connected to that. So this is a CH2 right here, two hydrogens there. This is a CH, only 1 hydrogen there. and this is just a carbon with no hydrogens at all. So if it has one carbon connected, it's a primary. If it has two carbons connected, it's a secondary. And if it has three, it's a tertiary. And that's the same with halides as well. With amines, it's a little different because we talk about what's directly connected to the nitrogen instead of what's connected to the, sorry, you can't see that, instead of what's connected to the carbon next to the nitrogen. All right. So that's all the new stuff for now. Just a couple things about dates coming up. So I have everything set to be due on Tuesday, so right before the break. However, the idea here is that I don't want people to be working too hard on this stuff during that break. I know the semester's been something, and we could all use some time to catch up and not just be barreling forward. So I want you to have that time to catch up. That said, you don't have to get everything in by Tuesday. If you want to use some of that time next week to finish mastering chemistry, to work on the labs, whatever, you can. I won't mark things down for being late if you want to turn them in anytime during that week. For me personally, I don't know how you work, but for me, if the due date is Sunday, I'm going to be working on it until Sunday. If the due date's Tuesday, it's going to give me some incentive to get it done by Tuesday and actually have some time to relax. But if you want that extra time, take that extra time. That's fine. Especially because we won't even be getting to the reactions until Tuesday morning. There won't be any other additional new stuff. There won't be any extra virtual lab or anything like that next week. It'll just be either the continuation of this if you're still working or just a break. If you have old mastering chemistry that you still want to finish, you can do that too. I'll still give you credit for that. The only kind of older things that I'm not going to give you credit for are pre-labs from when we were in lab, because those were supposed to be done before you come into lab, and quizzes. Yes, I would be happy to explain the grading system with Mastering Chem. So with Mastering Chem, again, I'll accept any homework at any point in the semester. So if you miss some assignments and you want to catch up on those, go ahead. That's a great way to study for the final anyway. Okay, let's do it this way. If you look at your grade book in Mastering Chemistry, it's not going to look the same as what's in Blackboard. And the reason for that is that 80% is the maximum score you can get in Mastering Chemistry. That counts for 100. So if you got 80% on a particular assignment or higher, then your score for that assignment in Blackboard should be 100. If you got below 80%, it's your percentage taken out of 80%. So let's say you got 76% on a Mastering Chemistry assignment. So in Blackboard, that should really translate to 90 something, right? Because it's not much less than 80. So that's the grading system with Mastering Chem. You get anything above 80% counts as 100%. All right. So then, so we'll be working on this stuff throughout this next week. Definitely practice the organic. You can work on the quiz as well. I think I will actually just move the quiz to being due that Sunday before we come back, so a week from Sunday, just to give you that time to kind of work on this, because this is new stuff. And then we'll come back from there, and we only really have 2 weeks after Thanksgiving, and then final exam. So we'll do biological molecules, and we'll be done. That's it. Did anybody have any other questions? Did you have any trouble getting through the acid-base virtual lab? I recorded a video, but I was having some technical problems, so I don't know how well it came out. I haven't had a chance to look at it again yet. Anything else that you all need before we go tonight? Yeah, go ahead, Alyssa. right, let me see if I can pull that up here. Post lab question 3. Oh, yeah. I'm sorry. I did see your message on this. Yeah, that is wrong. Um, assume that one is one and one is the other one. Um, well, that still doesn't make sense. Hold on, let me look at that again. Yeah, I did see that on Discord. So it says solutions of baking soda and boric acid were prepared. When 2 drops of malachite green indicator were added to the baking soda solution, it turned blue. When 2 drops of bromothiamyl blue indicator were added to the baking soda solution, it also turned blue. Which solution has the higher pH? That doesn't make sense, right? Because they're the same solution, so how could one have a higher pH than the other one? So let's see. So malachite green turns blue like in the neutral range basically, and then kind of clears up in the basic. And then bromothiamyl blue turns blue in the basic. In the basic range. So that doesn't make any sense. I'm gonna have to rewrite that or something. I don't even know what I'm trying to like reason out what it might have been supposed to mean, but it doesn't make sense. So just hold off on that for now. You can't answer that one. I'll talk with the other instructors and see what we actually meant to ask there. Yeah, okay. I think it's this. Yeah, I can redo the video about the experiment. But so for this particular question, I believe the idea is that one of the two is supposed to be the boric acid solution. So one is the bromothiamyl blue solution, one is the boric acid solution. But the rest of it makes sense. The malachite green turned blue, the bromothiamyl blue also turned blue. Which solution has the higher pH? And the answer is I'll let you think about it a little bit, but it's not really one or the other. It's a more complicated answer than that. Like you can't really necessarily distinguish it, and then you can talk about why. But I think it is just a typo there that one of them's supposed to say baking soda solution and one of them's supposed to say boric acid solution. So I will see if I can fix that, and then I will plan on recording a new video about the lab tomorrow. And then you still got over a week to complete it if you want, or you'll get it done by Tuesday. I think once it makes sense, it really shouldn't take you too long to complete the lab. But I will re-record the video for you. All right. Other questions? We have to be able to type numbers. Is your keyboard broken or something? Oh, you mean like to map the thing? Does that not work on your computer? Yeah. I can no, yeah, I can make sure that you don't have to do that. Yeah, Daisy had issues with that too. How did you end up solving it? I can't remember what we did. It was something about clicking directly on the A1. Okay. I don't know about these fancy Apple computers. Okay. Sorry. Yeah, sorry I can't help you there. Excuse me. I don't think we need to have one of those on the quiz. So I got your email about the other one. That's fine. Other questions? All right. Well, you know how to find me if you need me. Otherwise, I will see you Tuesday morning. And yeah, stay safe, stay healthy, and talk to you later. Bye. Thanks, everybody. Yeah, have a good night.